Hello and welcome again. Today's episode of CheM 3 is recorded in front of a live classroom. Let's go in and take a closer look.
Give you two pieces of data that you don't really have to use in the calculation. They give you this information here, 300 Kelvin, and they give you this, the size of the container. Because you need to know that those things are held constant. Because if pressure, which is the same as the volume of the container, if that's not held constant, and if temperature is not held constant, then what's going to happen is Kc could be variable. So that's to tell you that you're going to have a valid answer for Kc, the equilibrium constant. These two pieces of data get included. The real data that you then must use to solve the question are these three up here in red, and this piece here in red as well. So we're following this method which people sometimes call the ICE method, the ICE, where we look at the initial concentration, the change, and the equilibrium concentration. But the first piece of guidance that you have to get in solving questions like this, don't go into the question without having a balanced equation. Very often in the exam, the equation is given but it's not balanced. They've given it to you like this also, which is not balanced, and you could really be misled to thinking, especially because you're seeing 2 and 2, that this is a balanced equation. But if you examine it closely, you realize it's not balanced. You have 4 hydrogens here and only 2 here. The balanced equation is going to give you the mole ratio. That's the point of balancing an equation. And you have equilibrium. When you have equilibrium, by the way, what does that mean about the forward and the back reactions?
The rate of forward reaction is the rate of the back.
The rate of the forward and the back are the same. Does it mean that the concentration on this side is the same?
It's constant, but it's not the same.
Right, the concentration doesn't have to be the same.
Yes, it doesn't.
Why is it important that we talk about the pressure being constant and the volume being constant? Because those things
Affect the
Equilibrium will shift and you will have different concentrations.
What else can shift the equilibrium besides pressure?
temperature.
Temperature is already here. Besides temperature, besides pressure, volume of the container. What else?
Concentration gases.
The number of moles of the reactants or the products.
Changing the concentration of either one.
What about a catalyst? Would that do anything?
It doesn't know.
Catalyst changes the rate though,
Yeah.
but it doesn't affect the position of equilibrium. It increases the forward and the back reactions to the same extent. But at equilibrium, the rate of the forward and the rate of the backward reactions are equal. So the initial concentration of NO is 0.1. The initial concentration of H2 is 0.051. The initial concentration of water also is given, 0.100. What could be confusing in this type of question too is that this has been given and it's not a reactant, it's actually a product. And the other information that's given is that at equilibrium you have 0.062 moles per TM cube of nitrogen oxide. So that goes in here. So what was the change? The change was from this, which was the initial, by this much, which was lost, to give you this. So at equilibrium you have that, and that has, in the balanced equation, a 2 in front of it. So that is what you have at equilibrium. You have this amount, and it means that how much went into the reaction? This much went into the reaction. Now, if this is 2:2, and 0.038 was lost from the NO, because the ratio is the same, 2:2, 1:1,
Doesn't matter.
then it means the same number of moles of hydrogen is lost, which is 0.038. And then you can figure out what the equilibrium concentration would be, because this was lost, so at equilibrium you end up with this. Then, over on the nitrogen side, how is it that I'm coming now with plus 0.19? Based on what?
By 2.
This is 2. This is what is being lost by this, and it's going on this side. And because it's a 2:1 ratio, then on that side what will be gained is 0.019. So at equilibrium, so the change is this, and because this began at 0, then at equilibrium it's going to be 0.019. And for water it's going to be why 0.038? Because in the balanced equation, 2, 2, 2. So whatever moles of this was lost on this side has to be gained on that side by water. So then you have this plus this, which was the initial concentration, and you get this as the equilibrium concentration. So once you use the ICE method and you find all of the equilibrium concentrations, this is the second step. The third step now is to construct the equilibrium expression. In constructing the equilibrium expression, another common error is we see a 2 down here and we say this has to be raised to the power of 2. But why is something raised to the power of 2 or 3 or whatever? It's because of this value in front of here, the coefficient. And all of these actual concentrations in moles per dm³ are the values that will get plugged in here. So 0.062 will end up going down here in the denominator, and 0.019 will end up here in the numerator. And then you solve. You end up with an answer of 557. Another important point to note is what's missing?
The units. No.
Units are missing, and it's supposed to have units missing, because equilibrium constant is what we call a unitless
Constant.
parameter.
Yeah.
Doesn't have any units.